Hi everyone, I'm Yoshi Mariyama from NEC Solution Innovators. I'm a director of R&D and responsible for EMI stream development.
Hi, I'm Yoshi Fukawa from TechStream, US distributor of EMI Stream based in Silicon Valley, California. We are Team W Yoshi. Today, Team W Yoshi will talk about eliminate EMI problems at the design stage, robust EMI design rule check, and the plane resonance analysis at your desktop. So let's get started with the technical presentation first from Yoshi Mariyama from NEC. So Yoshi, take it away.
Thank you for joining this session. Finally, very important EMI design rule check and plan resonance analysis are available in the Altium Designer environment. This talk will show you how bad EMI design cause serious EMI problems and how to mitigate EMI using EMI design rule check and plan resonance analysis. We will explain some of the most important rules with simulation and experiment results. Before this presentation, let me introduce myself. I'm Yoshiaki Mariyama from NEC Solution Innovators. I have been developing EDA software for 19 years and I studied EMC technology to make our software better. 12 years ago, I was certified as an EMC design engineer by KEC and INALTE. Now I keep running so as to serve as an EMC committee member for JEEP. JEEP is the Japanese Institute of Electronic Packaging, one of the largest academic society in electronic packaging in Japan. I submitted several joint papers to JEEP. Today's presentation includes some excerpts from the paper submitted to JEEP in 2007. As you know, NEC is a giant company in Japan and develops a lot of products as below. However, we were facing a lot of real-world EMI problems with these products. EMC engineer sometimes had sleepless nights at the chamber for researching EMI factors and fixing the problem. So we started investigating EMI root causes with the EMC teams from different divisions in NEC. After investigating over 150 EMI root causes, we did reach most important EMI root causes. There are mainly two EMI root causes. One is related to EMI design rule on PCB, and another one is related to power plane resonance in between power and ground plane. Please take a look at the below chart. As for EMI design rule, we classified with three categories. First one is related to signal traces. The second one is related to return path discontinuity. And the third one is related to power and ground plane. Today, I will explain most important EMI design rules: return current path discontinuity, traces near plane edge, and decoupling capacitor, and show you their basic knowledge and how to solve EMI issue. I will also explain about power plane resonance, why plane resonance occurs, and how to mitigate the plane resonance to reduce EMI. Firstly, I'll describe the basic knowledge of return current path. The ground plane near the signal trace must be continuous. The nearby ground plane is the path of the return current. If the return current path is discontinued, EMI noise may occur. This is an example of single-ended signal. There is a signal line on the top layer. It covered with the whole ground plane on the second layer. If current which frequency is less than 1 MHz flows into trace like this arrow, return current flows into the shortest path in ground plane like this dashed arrow. In the case of frequency is more than 1 MHz, return current flows into ground plane along with signal trace like its shadow. This is a case that traces across the street on a plane. If a high-speed signal trace crosses over a street, return current detours along the edge of the street. This detour is called return current path discontinuity. It makes EMI noise larger. In this slide, I'll explain the behavior of near field in the case of return current path discontinuity. This test board is two-layer. The top layer has IC and signal trace. The bottom layer has ground plane. And there are streets on the ground plane here. High-speed signal is crossing over the street. This shows the near-field behavior on both sides. We can see the return current flows along with the trace and the edge of the street. The magnetic field is expanding from the street. This will be a critical noise source. Basically, the magnetic field occurs only between signal trace on the first layer and ground plane on the second layer. But in this case, the magnetic field is diffused from the street to the back side. This was a very interesting measurement result. The spread of this magnetic field shows a strong electric field intensity in the far field as common mode noise. This is the result of far field. The measurement result when the street width of the ground is gradually expanded is plotted. The black line is the radiation level in the case of no street. That's an ideal condition. As you can see, the longer street width, the stronger electric field strength can be observed in far field. The red line is the radiation level when the slit is 10 mm. That is, the return current turns 5 mm. The result of no slit, black line, and 10 mm slit, red line, are the almost same in the far field. So, the return current path discontinuity check of EMI stream allows the detour load within 5 mm by default. This is a case of 6-layer PCB. On the left side, signal trace runs on the top and fourth layer. It goes through a beer. There are ground plane on second layer and power plane on fifth layer. The return current path flows mainly the nearest plane from the signal trace. So the return path of top layer flows into the second layer, and return path of the fourth layer flows into the fifth layer. As a result, return current path doesn't continue between second layer and fifth layer. The right side is the case that signal trace runs on the top and third layer. In this case, the return current runs only second layer because the nearest plane of signal trace is the ground plane. Therefore, return current path continues. To compare with the far field, we can find the right side is better than the left one. How about adding a capacitor near the signal view? By adding a capacitor, the return current continuously flows through a capacitor. As a result, the radiation level becomes smaller than the left case. So it is important to keep the shortest return path as possible by improving layout pattern or adding a capacitor. That is an explanation of return current path discontinuity. EMI stream automatically can detect this layout pattern. For the next, I'd describe the basic knowledge of traces near plane edge. High-speed signal must not pass through the edge of the ground plane. The return current of signal flows through the edge of the plane, exciting the entire plane. As a basic knowledge, I will explain the return current distribution of signal trace. This figure shows a case where the signal trace keep enough distance from the ground plane edge. In general, the return current of signal trace flows from the area three times the width of signal trace on the ground plane, directly below the signal trace, like this figure. In this illustration, the distribution of return current from the center of the signal trace is symmetrical because the signal trace has enough distance from the edge of the ground plane. On the other hand, if the signal trace is close to the edge of the ground plane, some of return current flowing through the ground plane will be missing, as shown in the red section of this figure below. As a result, straight current occurs at the right end of the ground plane, exciting the plane. Because the ground plane itself has a dipole antenna structure, this electrical energy causes radiation. This is the result of simulating the distance between signal trace and ground plane edge and electrical field intensity in the far field. The far left of the horizontal axis is 0.1 millimeter, which is when the signal trace is almost at the edge of the plane. From this result, it can be read that the radiation noise decreases as the signal trace is away from the edge of the plane. From this, after confirming the quantitative reduction effect by simulation, we, NEC, decided the design rule of 2 mm from the plane edge as a realistic value. In other words, the design rule is that signal trace should exist further than 2 mm from the edge of the plane. EMI stream automatically detects patterns that violate this rule. The last rule is decoupling capacitor. The capacitor must be placed near the IC power pin. The closer the capacitor is to the power pin, the more effective it is. First, I will explain the noise flowing from the IC to the power and ground. There are two types of high-frequency current which flows into the power and ground of IC. The first type is the discharge current, the current flowing through the signal trace. This is an example of equivalent current for driver IC in a CMOS structure. When the signal becomes from low to high level, current flows from the driver IC's power pin to the signal trace. And when the signal becomes from high to low level, current flows from the signal trace to the ground pin of the driver IC. When the signal operated, it flows between the power and ground as a noise source in this way. The second type is feed-through current flowing from the power to the ground. Variation in the input voltage causes the signal to go from low to high level or from high to low level. At the intermediate potential of input voltage, there is a time when both P channel and N channel are turned on instantaneously, at which time high current flows from the power to the ground. These two types of current allow the noise current to flow between the IC power and ground pin. A capacitor is placed to suppress noise source between power and ground, which is called decoupling capacitor. Discharge current and feed-through current from IC, and by adding capacitors, you can separate the noise from the main power and prevent noise from flowing out to the main power plane. Decoupling capacitor can supply the electric charge required for discharge current and feed-through current, preventing noise diffusion near the IC. At NEC, it is our internal rule to place capacitors within 5 mm of the IC pin. So far, I have explained the impact of the far field caused by return current path discontinuity and traces near plane edge, and the basic knowledge of decoupling capacitor. High-speed signal required a continuous return current path. However, return current load shorter than 5 mm is acceptable, and it is also effective to arrange capacitors to keep the return path. In addition, it is recommended that high-speed signal be routed at least 2 mm inside the plane edge. Decoupling capacitors must be placed near IC power pins. Manually checking these design rules can be time-consuming and costly. Therefore, automation with a design rule checker, such as EMI Stream, is essential and effective in the actual design workflow. Next, I will explain the basic knowledge and verification result of plane resonance between power and ground plane. Generally, there are various antenna patterns in PCB. Single-ended signal behaves like a loop antenna. PCB and its cable behaves like a dipole or monopole antenna. A slit on a plane behaves like a slot antenna. Power and ground plane facing each other behaves like a patch antenna. Plane resonance between power and ground will be one of the dominant factor for EMI. When the resonance frequency of antenna accords with the noise source, the emission noise is strongly emitted. We can think simply, noise source multiplied by antenna factor equals strength of far field in each frequency. Regarding the noise source, ICs and high-speed signal traces are the dominant noise factors, but there is a limitation to suppress the noise source factor. Regarding the antenna factor, a pair of power and ground plane is one of the large antenna in PCB, and its factor is controllable. Therefore, it is important to calculate the resonance frequency in advance and reduce radiation efficiency as a patch antenna at layout design stage. The resonance frequency of parallel plane can be obtained with such a simple formula. In this formula, the plane has A millimeter horizontal length, and vertical length is B millimeter. And M and N are the natural number of 0 or larger. For example, suppose that A is 300 millimeters and B is 200 millimeters. And the mode of N and N, MN mode, is calculated. In 1-0 mode, resonance frequency is 220 megahertz. It is antinode, node, antinode in the horizontal direction of the board. In 0-1 mode, the resonance frequency is 345 megahertz. It's antinode, node, antinode in the vertical direction of the board. From this color gradation, you can see that the wavelength in 0-1 mode is shorter than that in 1-0 mode. When the resonance frequency increases in this way, it resonates with a complex voltage distribution. It is possible to calculate resonance of such a simple rectangular plane, but in actual PCB design, the plane has a more complex shapes. Another calculation method is spice analysis by using peak method. In this case, cutting the voltage plane and ground plane into mesh panels and converting to LCR models in each mesh. For capacitors on the plane, they are converting to LCR model, including ESL, ESR, with pulling out traces and vias. Then they are connected to the nearest mesh node. After that, it applies 1 volt and 50 ohms in series as noise source. By using sparse analysis, it calculated maximum voltage in each node for each frequency. By displaying the result of each node on the layout screen, it is possible to visually check the antinode and node of resonance. This graph plots the maximum voltage value for each frequency based on sparse simulation results. In the graph, where the horizontal axis is the frequency and the vertical axis is the voltage level, the frequency with the peak becomes the resonance frequency. In the plane resonance analysis, it is possible to show the high sinking voltage area in each resonance frequency on the layout display. As a countermeasure against resonance, place the capacitors at the hot spot. This reduces voltage variation between power and ground plane. By checking the gradation of the voltage distribution for each resonance frequency and adding a capacitor at the position of resonance antinode, resonance countermeasure can be easily implemented for anyone. In actual PCB design, if such a simulation is not performed, capacitors may be placed at a rate of several tenths of millimeter intervals on a design rule basis. Because placing too many capacitors increases manufacturing cost, it is a good idea to use simulation to consider the minimum number of capacitors required. Finally, I'd like to introduce the use case of plane resonance analysis. This is a 4-layer board with a length of 90 mm and width of 154 mm. The second layer is a ground and the third layer is a power. It is a simple board with a circuit in the upper left of the board and excites the power and ground at 33.3 MHz. There are parts in the four corners of the board where capacitors and RC snubber circuit can be placed. RC snubber used a small resistor in series with a small capacitor. This is a case of changing the resistance value of the snubber circuit to verify the optimal resistance value. This is the result of comparing resonance analysis by EMI string with near-field measurement. As a condition, the part in the four corners does not have a capacitor. Firstly, we confirmed that resonance frequency and voltage distribution match in simulation and actual measurement. This is the result of far-field measurement. We measured 5 cases. The first is a case where nothing is mounted in the 4 corners of the board. It is the same condition as the previous near-field measurement. In the second case, 0.1 microfarad is placed in the 4 corners of the board. In the third case, snubber circuits are placed in the 4 corners of the board. The snubber circuit is a series circuit of 0.1 microfarad and 1 ohm. In the fourth case, resistance value of the snubber circuit in the 4 corners is 5.1 ohm. In the fifth case, resistance value of snubber circuit in the 4 corners is 22 ohms. Since it is difficult to understand when the 5 measurement results are displayed as they are, we changed it to the line graph with 33 MHz multiplier. In conclusion, there was no common resistance value that led to good results at all frequencies. For example, at 166 MHz, the lower the resistance, the less radiation noise. On the other hand, at 900 MHz, the lower the resistance, the higher radiation. In this case, it is required to determine the resistance value according to the specific frequency to suppress. This is the result of spice analysis by using peak method. In this graph, where the horizontal axis is frequency and the vertical axis is impedance between power and ground, the frequency of the peak becomes the resonance frequency. The result, where there is no snubber in the 4 corners in the red line of this graph. By placing a capacitor of 0.1 microfarad, the resonance frequency is shifted to the higher one. By adding a resistance of 1 ohm in series, the quality factor is lowered. This is because the high-frequency noise current has changed to the thermal energy due to resistance. In addition, if the resistance value is increases to 5.1 ohms, the resonance peak decreases. When the resistance value is set to 22 ohms, the impedance of snubber circuit increases. So it approaches a state where there are no snubber circuit. By using spice simulation, it is possible to easily try and error the constant of the snubber circuit. This is the result of comparing the frequency graph of the resonance analysis with the actual measurement of the far field. As you can see, if the dominant factor of radiation is the plane resonance, it can be correlated with the actual measurement of the far field. In the actual design, it is necessary to perform simulation in advance to control the resonance between power and ground. at the layout design stage. Today, I explain the important design rules: return current past discontinuity, traces near plane edge, and decoupling capacitor out of 15 EMI rules, and basic knowledge and verification result of power plant resonance analysis. Now, EMI design rule check and plant resonance analysis are available in Altium Designer extension. From now on, Yoshi Fukawa will start the demonstration of EMI stream extension. So Yoshi, take it away.
Thanks, Yoshi, and it's Yoshi again from TechDream. As Yoshi explained, this EMI design rule and a plane resonance analysis are very important to mitigate EMI. So NEC developed and commercialized EMI stream back in 2002, more than 20 years ago, but now EMI stream is available in Altium Designer. So if you open Altium Designer, you will find these extensions and updates. You can find these EMI stream extensions with the EMI design rule check and applying resonance analysis. So after downloading these EMI stream extensions, you will find the EMI stream in tools menu with the EMI design rule check and the applying resonance analysis. So let's take a look at how to solve EMI problems with this EMI design rule check and the plane resonance analysis. So I will show you EMI design rule check first. So if we go to Tools, EMI design rule check, automatically converting into a ODB++ file and the opening EMI stream. So this is the EMI stream opening screen. If we go to edit and stack up, this stack up was automatically imported from Altium Designer with thickness for each layers and the DK and the DF tangent. So you don't need to set anything, actually automatically imported from Altium Designer. And then there are two another setting wise net property and another wise component property. So if we select net property, this is the net list from Altium Designer. So we have to set the frequency for only high-speed critical nets like clock nets or address bus or data bus. So just for example, I gonna set the 150 megahertz for this high-speed IO. I can just copy and paste for other IO nets. And then we also have to set the voltage. This power plane 1.2 volt plane, 1.8 volt plane as in power net, as in V, and another ground net as in G, set to G as in ground. And then if you have any other signal guide trace or differential pair trace, we can set it here. And just a set property. And we have very cool feature for set associating rules with a different reference designator. So if we have a reference designator like a C something, U something, R something, EMI stream automatically recognize this component and set as in a connector, capacitor, resistor, same as net. For example, if your net name has a GND or G or VCC as for power, EMI stream automatically recognize and set to ground or power plane. And the same as differential pair, if your net name has a PN or plus minus for differential pair, EMI stream automatically recognize and set to the differential pair. So setup is very simple and very fast. So now actually it's ready to check. And then we have parameter GUI for each setting. So this is a 15 EMI design rule check, including trace length check and via count, trace near applying edge check, as Yoshi explained before, and this is the reference change check, and return current path discontinuity over split plane, signal guard trace. Estimated radiation has actually this equivalent circuit model and predict the EMI from a loop area. And then signal guard trace via a spacing check, grounding via a long plane check, or filter check, and decoupling capacitor check is also important, as Yoshi explained earlier, and the differential pair check, length difference, parallel check, impedance unbalance check, and phase check. And we also have a crosstalk check and a digital analog interference check, overlap check, and the IC ground split check. So you can rely on these threshold parameters to for pass-fail analysis. But if you have any internal design guideline, you can of course customize these threshold numbers. But if you don't have, you can rely on these default parameters. These parameters were already investigated by NEC using simulation or experiments. So now it's ready for simulation. You can just click EMI rule check. So now checking all 15 rules at once. So this is a check result with actually a color gradation. Actually, red color has higher risk for EMI. So red, orange, green, yellow, blue. So actually we have a error point system. Higher error point, higher actually error net has higher risk for EMI. So for example, this net, D out has 25 error points, including playing edge error or reference change error or return current path discontinuity errors. So if we double click this error, this leads you to the error location down here. So this is playing edge error. And then if we double click reference change, actually it leads you to the error location. But not only error location, but also error explanation why this is an error. So it's explaining why it's error, but not only error explanation, but also giving the solution how to fix this problem. So actually you can pass these solutions to the PCB layout engineer to fix this problem. So same as return current path discontinuity. This is over split plane and return path discontinuity over the split plane, over the split plane. And then this is a error actually filter features. So you can turn them all and you can just see the for example, I already explained applying edge, return current, path discontinuity. So I can just select estimated radiation. So, and then double click. So this is actually estimated EMI from this loop area using this equation. So you can see either differential mode plus common mode or only differential mode or only common mode. And then another one is the plane outline and check. So this is a ground plane check. If we double click, so EMI stream recommends to put the ground stitching via with a red circle locations here, 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 because if we don't have this, we don't have the vias, this portion becomes antenna to radiate EMI. So EMI stream recommends to put the grounding via with a certain via pitches. And then this is a decoupling capacitors. Yoshi explained earlier. It's very important. So if we double click here, so this one actually this IC and this is decoupling capacitor is kind of far from power pin. So EMI stream recommends to actually change this location. And also very unique feature is we can visualize the return current path because minimizing return current path for the decoupling capacitor is very important. So actually we can visualize the return current path. So it's very easy for us to um, identify the capacitor location is good or bad. So this is a capacitor, decoupling capacitor check, and this is a differential pair check. So differential pair check also important. If we double click, so the balance trace lengths match is very important. So this is a plus minus, and this inside trace and outer trace length is different. So due to skew, it causes EMI. So EMI stream checking this differential pair check. And then this is actually, we may have a lot of errors, but we want to prioritize the errors. So we have filter features based on the importance of each rules and the frequencies. So we can just edit these weight for each rules. For example, if you think reference change is very important above 100 megahertz, you can set this as a high priority, or actually you can specify mid priority or low priority to focus on only critical errors. So this is a filter features, and also we have a report generation features. We can create report, this report in Excel format. So that's all about EMI design rule check. Okay, so now let's move on to the plane resonance analysis. So if we select tools, plane resonance analysis, again, converting to the ODB++ file and opening EMI stream with plane resonance analysis menu. So same thing, just Stuckup already imported, and net property already imported, and the component property we we are using this capacitor model for each capacitor, but automatically we must import the capacitance model based on the part name or capacitance value. So you don't need anything to set for this capacitor model for resonance analysis. And then this is a four-layer board. In the power plane on the third layer, and the second layer is ground. So plane resonance analysis is between power and ground plane. So we have to specify the power plane first. So if we go to plane resonance analysis, first we have to specify the power plane. So this is a power 3.3 volt plane, and also we have to specify the reference ground plane. So this is the second layer ground. And then these parameters like dielectric thickness or copper thickness, DKDF automatically imported from Altium Designer. So you don't need to set anything, but you can also manually change these thickness. So you can play with a different thickness or different DK or different DF. And then if we go to option, this is a mesh size. We have to set the mesh size. So if we final mesh size can have accurate result but takes longer. And then we have to specify the component capacitor library and the minimum clock frequency and the maximum clock frequency. We may want to set the fundamental clock frequency here, and we sweep actually harmonics up to 1 gig. and then just OK, and then just run simulation. So as you can see, it's very fast with the peak method and faster spice engine. So this red portion has higher resonance. And if we take a look at the VF graph spectrum chart, so this we have resonance around 870 megahertz. So that is no good NG. So we have to reduce the resonance below threshold. NEC recommends below minus 10 dB. So now we can add these actual red highlighted components as a capacitor, decoupling capacitor. So we can just copy these capacitors, or we have very cool features to place capacitors automatically. So if we go to auto place, and we can select a capacitor model, either auto or fixed. But if we select auto, EMI stream automatically select optimum decoupling capacitor and place onto the optimum location to reduce the resonance below minus 10 dB and repetition 10 times and run. So now EMI stream is selecting optimum decoupling capacitors, usually lowest impedance capacitors to the highest peak. So actually EMI stream added three capacitors. So if I double click this capacitor, actually EMI stream added this capacitor in here. And then if we take a look at the spectrum chart again, so this is the original result. And after adding one capacitor and two capacitors, three capacitors, actually below or minus 10 dB to reduce resonance, then that is okay. So you must stream automatically select decoupling capacitors and place onto the optimum location to reduce resonance. And then you have, if we click component list, these actually the component decoupling capacitor list for this particular power plane. And we also have a far field EMI prediction estimation from PDN power plane structure, because power plane becomes patch antenna to radiate EMI from the edge of the PCB. So if we place the PCB onto the turntable, we can specify PCB position and the PCB orientation, like a horizontal or a vertical one or vertical two, and then we can specify distance to antenna, either 3 meter or 10 meter or 30 meter, or antenna height usually from 1 meter to 4 meter. I can just set the 1 meter and the turntable step we can set, and then okay. So this is actually a far field EMI from PDN structure. So we can see this vertical and horizontal EMI, and also azimuth pattern, radiation pattern. We can see the radiation pattern, which direction we can have EMI most. So we can compare with EMC chamber measurement result. So if these peaks are matching to the EMC chamber measurement, these peaks are most probably coming from the resonance between power and ground plane. So we have to reduce actual resonance to mitigate EMI. So that's for the power plane resonance analysis. That's conclude our presentation and demo. If you have any further questions, please visit our virtual booth at AltiumLive. We also have 1 month free trial license. So if you want to evaluate, please let us know. Thanks for watching and have a great day. Bye bye.